This is where I normally keep my coffee.
Welcome everybody to day 3 of the ICM workshop. We are happy to have Zander Kelley giving us a 2-lecture series on structure versus randomness.
Great.
Lecture 1.
Great. Thanks, Prahlad. And thanks to everyone responsible for organizing and combining these two nice workshops. And I guess good morning, everyone. Thanks for your interest in my talk specifically. Great. So I'll tell you about structure versus randomness at like a pretty high level, mostly aimed at people maybe less familiar with it, at least for this first lecture. And I guess here's the plan for the talk. First, we'll go over kind of the rough paradigm, which is like, we'll really look at this at like a very high level because in some sense, it's the topic, structure versus randomness, it's like not about anything. Like there's no specific subject matter that we're studying. It's like more like a collection of techniques, tricks, philosophy, if you like, that you can try to apply to many different situations, and then we'll see some, I'll show you just briefly some lists of applications to theoretical computer science and also to extremal combinatorics. Then we'll go over this, which I think is like a really compelling, we'll talk about this problem, finding 3-term arithmetic progressions in dense sets. It's like maybe like the poster child problem for the technique. And it's a like really nice self-contained problem where we can discuss it like from end to end what you're trying to do with this kind of technique or philosophy. And then at the end, I'll talk about like constructions, like algorithms, decompositions, partitions of arbitrary objects into some like nice structured parts, mostly focusing on the actual like constructions themselves. And then the next lecture we'll talk a lot more about something that makes up like maybe more of the technical bulk of the topic, which is just comparing different notions of pseudorandomness and showing that some notion which is given to you by these regularity decompositions, which maybe a priori looks like it's offering you some pretty weak form of pseudorandomness, it is actually useful for some applications. So great, so let's get started with this first item here, just the basic paradigm. So what is that in like one picture, like a whimsical one? This is the whole story. So the setting here is like we want to try to understand like arbitrary, you should think worst case objects, inputs like graphs, sets, functions. And that's like in contrast to other talks in this workshop, like where we're focused on, explicit constructions of pseudorandom objects. Like you get to like pack your own lunch with your favorite pseudorandom object for the application. That's like not the case here. So we're really trying to be like prepared to deal with like we want to use pseudorandomness and we want to use it on like arbitrary, dense graphs, say, like with a large number of edges. And specifically, we want to like not every graph is pseudorandom, so we can't just to use it in the like most naive sense. We need to decompose it. We want to decompose it into some like highly structured parts and some like certifiably pseudorandom parts, notably trying to like avoid anything in the middle here. Great. Okay, so maybe some like more concrete, down to earth instantiation of this picture. It's like this picture from real analysis. Like we're familiar with this idea that you can take some like arbitrary function, try to decompose it into some like part that's simple. You can interpret it as like the signal, and some part that's like hopefully small and you're not so interested in, interpret it as the noise, and we want to try to like cleanly separate these two. And great, so this is a good picture to keep in mind. Usually we're going to be talking about some like spaces where it's really like less clear what it really even means. So I want to like ask you to think about this kind of general question, like to what extent is this idea that I showed you, like the signal versus noise decomposition of arbitrary mathematical objects, like how general can you make this? Like how far-reaching does it make sense? Or like does it make sense to apply it to more abstract situations? So you have to answer these two little questions certainly for this to make sense. You know, you gotta say like what's the notion of structure that you want to define and work with, and then you know something that probably people in this workshop are pretty familiar with, but it's definitely like necessary for this kind of paradigm to make sense, is like how do you quantify randomness in some fixed deterministic object? Like we don't actually have a random graph, we have like one fixed graph, and like what does it mean to discuss whether that graph is random-like? Great, so yeah, okay, and here's something related to this last point. So I want to say, yeah, like start to give you some high-level intuition about what I think are some situations this paradigm applies to. So one thing it does is it kind of gives you some way to try to justify the idea that like, you know, these three pictures, which are just some like static noise, you'd really like to be able to say that they're basically the same. Like, you know, you can see some differences up here. You can't see any interesting differences down here, but I mean, I hope you appreciate like if you just wanted to sit down and actually write down some formalism that actually justifies that it's not so easy. Like, you know, if you just literally counted like the number of different pixels, say, between the two pictures, you know, maybe these are all as different as these. So that's some reason to be interested in this. We'd really like to have some framework where it makes sense to try to say, okay, these are all really just like the random picture roughly. Okay. And then, yeah, so here's some elaboration on this. Like, what does it mean to think about, you know, randomness for a deterministic object? So here's something, you know, just a bunch of fun facts about like a random graph GN1/2 that hold with high probability. Okay, and then so it's true that if you just draw like some random graph from GN1/2, all these hold with high probability. So you could say like, you know, what is a deterministic graph that's pseudorandom look like? Well, it should just have all these features. Like you know, the chance that it satisfies all of these is like overwhelmingly large. You can afford this, you know, union bound if you pre-commit to like some reasonable, you know, number of hypotheses that you want to satisfy, and then it makes sense roughly, you know, for anything that you can prove happens with high probability with over an actual like random draw of a random graph to use that as like a definition of pseudorandomness. And then like, yes, so why, also why would you be interested in doing this? Like, so sometimes we're going to talk about problems that don't have any randomness to begin with, like not in their problem statement. So what's good about the random graph? So the thing that's good about the random graph is we know everything about it. Okay, so that's something you should keep in mind. Like that's one of the goals, or like one of the outputs of this is that like if you can show that your graph behaves like the random graph in you know one or more ways, then that's great because we roughly know everything about the random graph. Okay, so then, yeah, here I'll start to get like a little bit more specific on like the kind of thing that we're actually gonna hope to accomplish, especially in this talk specifically. So we're given some like arbitrary object. Like I said, it's some like, you know, you should think of it like adversarial, worst case. The thing we're always gonna assume about it is it's like high entropy. Okay, so that's like the assumption that we're always making. It sort of like doesn't make sense to, I think, essentially doesn't make sense to ask for the structure versus randomness paradigm to help you without this assumption. It's like important that your blob is like close to the uniform distribution in a weak sense that it's like high entropy. Okay, and then given this assumption, we have some like problem with some structure defined on it we already care about. And here I'm like the structure is like these rectangular atoms. Is what I'm drawing, depicting here. And we'd like to take the object and like decompose it into parts that are like roughly pseudorandom or very sparse with respect to these atoms. And then we can sort of say like that we've like managed to simplify our description of the object, like up to some small error. It's really like this simpler to describe object, just some union of like a small number of these structured atoms. Great, so that's like the general picture, like regardless of the structure. So here's some instantiation of this, like probably maybe the most famous specific like regular decomposition. It's Semreti's regularity lemma. Shows you if you take some like arbitrary graph, really like quantitatively, the graph needs to be quite high density, like maybe almost like constant or slightly sub-constant density to get some non-trivial statement. But for very high edge density graphs, then we can decompose the vertex sets into some clusters in such a way that like the bipartite graph between each pair of these clusters becomes either sparse or like spectrally pseudorandom. Like say measured by discrepancy or second singular value, if you like. And then what's the point of this is that the thing that's been accomplished is that we took this like arbitrarily large like n-size graph and we've like summarized its structure into some little in certain settings like constant sized graph that's like really showing you the signal that represents the graph, and kind of summarizing like this data with just some tiny bit of like constant amount of bits needed to specify it, say. So at least in applications where you're willing to say that like a good enough expander graph is like roughly like the complete graph. Okay, so great. Okay, so here's just some big list of applications in computer science. I mean, I think to warn you, like I guess to compile this list, I'm taking a fairly liberal interpretation. Like I don't know if the word structure versus randomness appears in very many of these, but yeah, we have a bunch of applications where we're doing this sort of thing. We're taking some like high entropy distribution, say over 0, 1 to the n, and organizing it into some parts that are like, say, blockwise dense is the notion they need for this last one here. I guess what I have in mind here is like this characterization of like non-expanding sets in like the Johnson and the Grassmann graph. And then, yeah, so we'll see some. Okay, the connection is not so obvious unless you have the background, but we'll talk about some like general kind of decompositions that are similar to this paper. I called it like plucking sunflowers. There's in this paper they do some plucking of some sunflowers, and we'll see what that looks like in a second. And yeah, I guess maybe I'll highlight one more here. I think there's a nice recent paper that uses some like regular decomposition to actually get very efficient like near linear time algorithms for list decoding. So yeah, so I guess something that will come up a lot is like for CS applications, usually we have to make some compromises. Like I think only a few places really can we use like the classical regular decompositions kind of directly. You can use them in this work on property testing for like very dense graphs. which is like the setting that's most typical for that problem. But usually, like, to be able to make some non-trivial statement, we can't afford to pay such a high cost as these, like Semirates regularity lemma has some, tower type dependence on the density of the graph. So that'll come up, and we'll talk about the comparing quantitatively later as well. And then, yeah, I guess I would say, I think it's fair to say, like, in a certain sense, like almost every paper on communication complexity is a good example of using structure versus randomness, at least in a reasonably liberal sense. So, okay, so great. So then, yeah, so here I just have also a big list of some, mostly I just picked like the big, boring, famous ones of problems in extremal combinatorics where this is like the main or only approach known to get like good answers to these questions. So if you're less familiar with extremal combinatorics, so unlike this earlier page where we just, in TCS, we are interested in doing like a bunch of just obscure things, I can actually say like what's going on in each of these. It's always like the same kind of story. At least one way I would describe it is that like what's your like prototypical problem in extremal combinatorics? You're given some like dense set, and you want to show that if the set is dense enough, then it's forced to contain some pattern somewhere. So like a triangle, 4-cycle in a graph, like a 3 point. So a 3-term arithmetic progression. You can just describe it as 3 evenly spaced points, like at least if you're talking about like in the integers. So you're looking for this pattern. You want to show that this is like unavoidable if the set is large enough. So it's some sort of, often these are like some kind of like succinct family of packing problems under some constraints, if you like, although I guess that's like the dual point of view of these problems. And it's not like obvious why this structure versus randomness is necessarily relevant or the most obvious approach for any of these problems. Like there's a lot of these problems that you can just kind of solve directly. So maybe a fair example is like determine the largest number or the number of edges that a graph can have if it has no 4 cycles. Turns out to be a pretty easy problem. It's roughly like n to the 3/2. And you can prove that just with some inequalities, just some Cauchy-Schwarz or something, and then you don't need fancy tools. But it seems like these tools coming from structure versus randomness, they're like maybe not the always quantitatively the strongest, but like the most flexible. They like apply to the most like the largest range of situations, and you can usually get them to say something. So that's some explanation of the sex of the method in this context. So great. So then we'll switch to like zooming in on this specific problem, like 3 APs in dense sets. That's what I want to pick as like a good illustration like of a specific problem where we'll just work through the whole things and see how it goes. So great. Okay, so I actually have maybe a little preamble to this problem I thought of specifically for this workshop. So I think it's nice to contrast this problem we're eventually going to talk about, which is for arbitrary dense sets, with this specific problem. It's like you can think, this is like a problem in number theory. You're given a specific set. It's like analogous to a pseudorandom construction. I guess analytic number theory is kind of similar to, in a lot of ways, with what we want to do in pseudorandomness in the context of TCS, like at least in the sense that there we usually would like to build any like explicit pseudorandom object. In number theory, probably you want to understand like some particularly natural pseudorandom objects, like the primes. But with that context, yeah, so let me just say, so here's this question, like do the primes contain, say, like infinitely many 3 APs? So this is some special case of like the Green-Tau theorem, if you've heard of it, which verifies this for k APs. We'll just talk about this case, k equals 3. And if you believe like this general, it's like a familiar heuristic kind of motivating paradigm inside number theory that like it ought to be the case that some additive structures and multiplicative structures, they kind of interact pseudorandomly. So if you just apply this heuristic, at least very naively, like what do we expect? We expect to see, roughly there's just like a delta cube chance that any like particular triple of points is a 3 AP. So we're not expecting that the primes contain like a surprisingly high number of 3 APs. We just want them to contain like the number you expect for any like random set. Yeah, okay, funny correction you need to do. It turns out like there's like a small bit of deficiency of the pseudorandomness of the primes with respect to the structure of this specific problem. You can think about where it comes from if you like. But it turns out this heuristic is only like a tiny bit off. So it's off by some little factor that's like 0.66. Yeah, so this was verified, like shown by Van der Korpit. It's like some classical analytic number theory that you can use known properties of the primes, like there's ways to measure and quantify their additive pseudorandomness to verify that this heuristic is true asymptotically. Great, so yeah, I want to say here, so here's one slide elaborating on this pseudorandomness, quantification of pseudorandomness I was talking about. This is slightly simplified compared to the prime case, but I want to show you just this theorem. So if you have some 3 sets, say of some finite abelian group, we need them to be dense. And we just need one of them to be additively pseudorandom in this specific sense, that it has like largest non-trivial Fourier coefficient is at most epsilon. So this is like, if you like, same thing as like bound on the second eigenvalue of its Kelley graph, that kind of pseudorandom assumption. Then the conclusion is that you can like predict, you can control the number of solutions to this equation A plus B equals C. It's very close, for the right parameters to just delta cubed. If all 3 of these sets have density delta up to some error. And sure, so here's the calculation. I guess I might talk a bit more next time about like how to think about how this calculation interacts and relates to some more familiar pseudorandom, like quantifications of pseudorandomness, but great. So this is just to show you like a specific calculation related to the previous setup, where we already assume we have some like nice pseudorandom object like the set of primes. Okay, so I think that sets up this question nicely in the following sense. So if you if you think about what did we learn, what does Van der Korpit's theorem say? It seems to say like the primes have 3 APs, and the argument shows like why is that? It's like because they're pseudorandom. That's the explanation. Okay, that's true. That's literally what happens in the argument. But here's a weird catch, which is like it seems like also sets with additive structure also have 3 APs. So like it's hard to find any like example that seems problematic is my point here. So you could think of like, for example, the most extreme structured set with respect to this specific measurement of pseudorandomness we were looking at. That like is it like approximately periodic with respect to some character? And that has no issue. Like there's plenty of 3 APs in this guy. It's like kind of isomorphic to just an interval again itself. So yeah, so that's like sets up this question maybe in a historical way, but that maybe every dense enough set has many 3 APs. And this is a question asked by Erdős and Turan in 1936. That they want to know, what density delta guarantees the existence of a 3 AP for arbitrary sets. Okay. Okay, so that's the question. Okay, so here are some 2 pictures elaborating on this kind of dichotomy we've seen so far. At least like this is the something we hope is some dichotomy that explains things. We talked about how like if you have some actually random or like even like additively pseudorandom specifically measured by largest Fourier coefficient, that's sufficient to just get 3 APs in your set just by chance. And then we can also look at like just some structured examples. So a good example to keep in mind is just some interval somewhere. Is like a good notion of an additively pseudorandom set. If you want some reason for this to like maybe to quantify it, one way to quantify or justify the fact that an interval is additively structured is that it's like approximately closed under addition in the quantitative sense at least. Like it only grows by a factor 2 instead of like squaring in size like kind of a general position set would. And okay, so I wrote down here like the dream, which is, I think, maybe it should come across as fairly naive at this point. Like we have these 2 extreme cases, at least they seem extreme. One was like the most structured thing we could think of. One was like actual random sets. We checked that both examples are fine. And then we're wondering like, maybe there's some reason that we could just prove it for arbitrary dense sets by some interpolation argument, okay? So yeah, an interesting like caveat to this is it turns out to be not like literally true. So it's actually not true that these are the most extreme cases. The worst numerical case for this question by Erdős and Turan is actually somewhere like pretty squarely in the middle. So some like geometric construction due to Behrend, but somehow, even still, like the structure of the actual argument that we're going to end up looking at does accomplish this. Like that's the qualitative way that we're going to prove the theorem, that we're going to get some bound on delta and find a 3P. So, oh, sure.
At the time of Erdős-Turan, did they have a lower bound on the density at which this was not true?
I think Behrend's construction.
Before 19?
I think. Oh no, I guess you're right. That took a while, huh? Yeah, I don't know what quality of lower bound they had before that. I suppose that I do know that you can think of there's a natural greedy construction where you just like go from left to right and you like include points, whenever you can. And you can like, funny enough, you can work out like some explicit description of this. It's like has a easy to describe, like the actual set of points this gives you. It's like easy to describe in base 3, turns out, and you can like work out that this is giving you some like polynomial density. So some like delta, which is like n to the epsilon for some constant epsilon. Yeah, which is not quite as good as Behrend's construction, but probably they knew this at least, yeah. Any other questions? Okay. Great. So yeah, let's try to set up like so why what are we going to actually try to use to make this dream come true that we just said? Well, we have these 2 cases, and right here I've like. I have in mind the same kind of quantification of pseudorandomness as we had earlier. Like you want to look at this like spectrum of your set and ask like whether all the non-trivial Fourier coefficients are low weight or not. So why is that? So it's related to the specific kind of structure I told you we were looking at. We were looking at like, all the even integers or all the integers equal to, 1 mod 5 or something. So we're looking at like residue classes and specifically like these histograms. And the point is that you can relate this quantity, like the balancedness of this histogram, pretty directly with the bias of the corresponding Fourier coefficient. And this gives you some plan. So this is like a plan due to Roth, which is like some plan to do some induction, say. What we want to do is just look at this residue class that's heavier than all the others, and just kind of zoom in on that. Like, so we just throw away all the other points. We like obtain a sort of self-similar problem. Like you can like try to convince yourself that it's kind of isomorphic with respect to what we care about, just counting 3 APs. The fact that we only have this periodic container set, which is some shift and scale of an interval. And then we think about just the set of points that lie in this set. And the progress we've made is that like we just have more points. So like at least if you're just quantifying things in terms of, say, like entropy deficit relative to the uniform distribution, like this set is more random inside its container set. Okay, so that's one way to think of like what progress has been made. And yeah, I think it's like a fairly humble kind of argument. Like at each step, you're not trying to do something clever to especially sensitive to solve this optimization problem, to like detect these 3 RPs. Like at every step, you're just looking for more stuff. And that's this is Roth's like introduced this approach on kind of simultaneously on this problem and also on the Heilbronn triangle problem like a year or so earlier. But yeah, like he had this very influential work, essentially introduced like this structure versus randomness method, at least like in the sense of how it applies to additive and extremal combinatorics. So here's like the argument. It's just to iterate this step I showed you on the previous slide. So at each step, we have this case analysis. Say, like we already know that if the current set inside our current container set is pseudorandom relative to it, then we can do the same kind of calculation, like say roughly that we did for counting 3 APs in the primes, quantifying pseudorandomness with this Fourier coefficient that verifies that you have many 3 APs. Of course, just only in this container set. So at the end of the day, something that's important is that like you stop before the container set like becomes a single point. So once you're a single point, the trivial 3 APs don't count. Okay, so you're not interested in those. You need to arrange things so that this algorithm terminates before your container set becomes just like some single point if you're looking for some non-trivial 3 AP. But yeah, so this is Roth's whole argument, and this is what his result was. Like the first kind of asymptotically non-trivial answer to the Erdős and Turan problem, obtained some density threshold, delta, which like goes to 0 as n goes to infinity. Great. Yeah, so tried to hide that detail a little bit, but you can do it over Zn. You'd have to worry about it. So there are some kind of ad hoc tricks to deal with it. Actually, in a sense, that's more like the more modern approach. Maybe the earlier stuff actually did work with literally like Fourier analysis over the integers. So that has its own complications that like I guess aren't described exactly here because you have to talk about all the characters, not just like some finite set of them. So you'll have to, it's not so easy to quantify it like the exact way I described here. But you can do this, like in the modern, certain modern presentations of it, you try to like embed, you go back and forth. You try to embed this interval carefully in like Zn prime for like slightly larger, and you can do this carefully and preserve the fact that, or like whether or not A has a 3AP when you consider it mod n prime or just in the integers. Any other questions? Great. Okay, so yeah, now time for the last part of the talk. So we're going to talk about algorithms. So we saw one algorithm in a sense. Oh, sure.
Where does the log n? Is it here? Where it's over here?
So the log n is blamable on the integer setting and the fact that it's more difficult. So if you ran this in like the finite field model, so if you tried to prove like the bounds for cap sets for finite fields, vector spaces like where capital N is equal to fq to the little n, then you would get 1 over log n density. So like just from this, like the exact argument I sketched here, there's nothing missing from that if you're in that setting. So otherwise, these like technical complications that come from the fact that you need to, in the integers, things are just hairier. You don't have like actual subgroups. You'd only have approximate subgroups. You have to do tricks like embedding and going back and forth. Yeah.
It should be coming. So the S case is exactly what you had proved you had fully presented. Feels like it.
Oh.
Yes. If it's random enough, you got it. So it's a question of how much is the density increment happening? How large is that? What is governing this?
No, I'm saying like there's okay. I think the specific loss is that to implement this like trick I said. So you need to like sorry. This is at least in some like modern presentation of the argument gets the same result. So I imagine it's faithful enough in spirit. But something that might happen at every step is like you make progress. And then to facilitate this transfer back and forth between the integer setting and like the Zn setting, you might have to pass to a container set which is size like square root n. Like in this step, you like preserve density, but you like give up size of your container set. So that like extra detail is what's costing you the extra log factor. Sure.
So let's say we weren't in the integer setting, just in the finite field setting, so you don't have to worry about that stuff. Which, it seems like there's two quantitative things in each iteration. One is how much the density increases, and another is how much n prime is smaller than n. Is one of those the dominant thing in determining the final quantitative result?
Well, you have to do the exercise. So I'm just kidding. I guess, okay, so here is a reasonable like setting of parameters to imagine. Let's see. So let's do what you said. So let's go here. So let's talk about A is here. And then I want to run this argument until I arrive at some A prime in some affine subspace V, which is like, let's say we try to stop by the time we're here, which is not giving up much, I guess. Like in a sense, once you've made this decision, there's no choices left to make. Like you're right. Like so you just care about this amount of progress you can make every time. In terms of the density, and there's no flexibility on like what you should do. Like before analyzing the problem, you can write down like the best version of the density increment thing that you could hope to get, at least this is like a way that I like to think about the problem, and then it just delivers, it delivers some pseudorandom property. Like it just tells you there's no, codimension 1 subspace that has more density. So that's like just, you can think of that itself as a pseudorandom property. And you can just work out the best version of itself that you obtain. Sorry, if that didn't quite answer your question, you could ask another.
Codimension 1, you're just decreasing the
yeah.
codimension 1 at each iteration.
At each iteration, yeah. In this like simple setting, yeah, absolutely. Yes, that's right.
Thanks.
Great. Okay, so yeah, we'll talk about some more general algorithms, more general constructions. Something I want to emphasize is that like, and I think that maybe if you look at the 2 exercises, you'll believe me what I mean by this just after like 2 examples. Somehow these are like generic. They apply to a lot of situations. I have not tried to like compile for you some like obscenely abstract like formal picture of exactly when they apply, but like I want you to think about them as like generic constructions you can use for like kind of general collections of nice sets that you consider to be your like structured sets you care about, like subspaces in this example, approximate subgroups, say over the integers. Like I guess in the graph theoretic case, you care about like induced subgraphs, like rectangles, I suppose, like cliques. Anyway, so the however, just for illustration, we're going to pick something concrete. So I want to talk about this situation where we have a dense set. A in just in 0, 1 to the n, just a dense subset of bits. And okay, so again, we make some density assumption about it. For like doing the quantitative part, it would be nice to think about the density in this logarithmic sense. So we're quantifying the density of A by its like entropy deficit relative to the uniform distribution. And yeah, I want to state this isn't like structure versus randomness necessarily, but it's some nice like point of reference that you can use to like compare. Okay, what are all these decompositions actually saying? Like, what are they giving you? I think each one is like nice to compare to this statement here. So this is it's like called the level 1 inequality in Boolean Fourier analysis. It's just this upper bound that we can look at like all of these marginals of the uniform distribution over A. And you can think of this as like some, maybe A is like representing some list of n arbitrarily, jointly dependent coin flips. And then this is like the bias of the ith coin flip. So this is like some very, very weak, but concrete measurement of failure to be pseudorandom when this quantity is large. So the level 1 inequality tells you this bound on the total kind of bias of all your marginals. So the sum of squares of all these marginal biases is at most O of D, where D is this entropy deficit. So another way to think of it, this actually is equivalent just by some, integration, I guess. If you prove it for all epsilon, like A has at most some D over epsilon squared bad marginals. Okay, so then, so here's the thing that I want you to keep in mind, to imagine. There's like a memorable tight example, like exactly witnessing this, it's sort of obvious, is that you exactly just have somewhere some like D bad coins that they're like completely fixed, completely deterministic, and then the other n minus D coins are like entirely uniform and balanced. Okay, and then like maybe if you're a mathematician, if you're a little greedy, you could hope like what, is this like in any reasonable, justifiable sense like the only case? Turns out not really, but like in some specific limited senses, perhaps. So that's a nice question you could have in mind when you interpret all these constructions. Just wanted to have some reference point to think about what's being accomplished. In each case, in a certain, like very weak sense, we're going to end up justifying some sense in which an arbitrary dense set can be decomposed into examples that look just like this. Okay. Great. Okay, so here, I just have some like quantitative parameters worked out, but the algorithm is the exact same that we just saw in this other setting. And the result, okay, so what is this theorem telling you? It's telling you that like relative to some container set, some structured container set, some like subcube that's defined by just fixing some R coordinates, like a restriction of them to some specific values. Like the restriction of A to this subcube becomes pseudorandom in this weak sense we set up before. It has all like balanced marginals. Okay, and here, so here's some quantitative stuff, like what can you accomplish with this? You want to know that it doesn't take too long. This like square doesn't get too small before this process terminates, and so you can get codimension R, which is like at most d over epsilon. Could compare that to the like d over epsilon squared quantity we looked at a second ago for the level 1 inequality, if you like. Furthermore, just by the structure of this density increment argument, like at no point does the density decrease. So you get it with this like extra promise as well. Okay, so that's some like very basic kind of construction where you just try to find one good part of your given set A. So here, now we'll look at like what if you wanted some decomposition, some like partition of your given set into some structured parts. So here, again, the setup is the same. What I would like is to find some like local restrictions onto some subcubes where on these subcubes, like either A is like very sparse there, so then we're quantifying like the total like error part is kind of summing up all the mass of A which lands in some part which is not good, which is either sparse or not pseudorandom. But then accepting this like small error set in all the rest of the subcubes that you obtain, you achieve this like pseudorandomness guarantee, this epsilon balanced marginals guarantee relative to the current container set. Okay, and then so we haven't seen the algorithm yet for how to do this, but I guess I should say here's the result. It's kind of interesting to compare to this bound from the level 1 inequality. But here is like just some simple algorithm that accomplishes this. So it's giving you a partition that more specifically has this like tree structure. So at the top I've drawn, like all these boxes are depicting like the marginal values. Like we want them to all be roughly half full. That's when we're happy. That's when like our set has been like kind of factored into some structured part and some pseudorandom part down here. Okay, and what can you do? So it's sort of, you could imagine it as like some greedy algorithm if you like. So what can you do? You can split, like on any particular bad marginal, I want to decompose. I go ahead and like partition the space with respect to that axis into two halves, and then continue like recursing locally on both sides. Okay, and might be less intuitive how to think about like in what sense are we making progress here. you could compare it to like the density increment accountings before. So it's true that like on one side the density increases, and then on the other side it decreases. So it's like maybe a small puzzle to think of a way to try to capture in what sense are you making progress towards regular decomposition. And like, I suppose a good way to think about it is that, yeah, in a sense, the parts that become sparse, if they become sparse enough, that's also like a good case for this decomposition. Like really what we're trying to quantify and like accomplish slowly, step by step, is to generate some like polarization. Like we want to force the parts to either like density increment, and then they're like kind of trapped against the upper bound wall of like their density can't increase past 1, or to like move in the other direction. We just want any sort of motion at all to push the partition to become more and more polarized as we refine it. So in the exercises, I guess like there's a bunch of options for how to specifically analyze this, but I wrote down something like particularly convenient that you can use to track some kind of like specific F divergence type quantity.
Are the brackets of this strictly better than the brackets in the... Does this subsume the previous result that we had?
No. So
Why not?
So here this bound is a little worse if you only wanted one part. If that was what your interest, if your interest was to find one pseudorandom part, then and this is a bit worse. There was d over epsilon in the first case. So you do pay something for.
This is the entropy deficit. So is that okay? Is this necessary? Is this gap inherent?
I believe it is. It might be hard for me to justify it easily now, but if you like, we could talk about it. Yeah, I believe it is. Any other questions?
What is almost all of A exactly?
So if you pull up the exercise, I have something very like the full version of this theorem written out. Just trying to suppress a few of the parameters here. So it's I guess like a nice setting to keep in mind that's like kind of I don't know, you might as well assume it in the sense that it costs you roughly the same as anything else, is that this error part is like in total it has density in the full space like say 4 to the minus d. And like I guess, okay, fine. Without seeing how it affects this bound, I guess that doesn't oh no, that does make sense. Like I'm saying the d parameter captures the dependence on both aspects if you think about it like this. Yeah. Any other questions on this? Yeah, so that's what I was saying before. So if you want a specific statement which is true, you could think almost all of A means, except for some fraction of A whose density in the whole space is like 4 to the minus d. But also the like exercise PDF has this worked out with some 2 decoupled parameters and shows the dependence with respect to both of them.
And then the final partition is one leaf of the decision tree?
No, it's like the whole thing is, so the whole decision tree, it's like all the leaves are the, that's your partition. So it's like kind of described in terms of this decision tree.
Oh, I see. So R we should think of not as the
Yeah,
depth, but
R is like the
number-
queries, yeah,
what
sure.
number?
A number of queries, the depth, yeah. Yeah.
But different ways down make different queries.
Mm-hmm.
So each in this tree, at each branch, you are fixing a coordinate, right?
Absolutely.
And so then the leaves, that's just your subcube. You fixed R coordinates.
Absolutely.
R.
Yeah.
Okay.
For applications, like why do you need a partition to space instead of just a set? If it was just a set, you could just iterate the one part version. Right?
Yeah, so that's true. So that's this one, this like next guy here. So you're saying, sorry, you're saying if you wanted to just get like a covering, or is that not what you meant?
Like, right, I guess like why can't you just iterate the one part version? I guess it's because the cubes will overlap.
Yes.
But is that a problem, or?
I mean, for certain applications, no, I guess. But yeah, I guess we could think about what that looks like maybe for a second here. So what's the issue? I mean, I could remove one of these cubes, like you're right. So what are we doing? We could look for a sunflower and we could pluck it. So that's what we're doing on the next slide. We're doing some sunflower plucking. But then now my like outer container set, it's like a different type of set. It's not like a cube space anymore. It's something else. So if you're like happy to pass to that, then you could. I think usually you're not. Like usually you want your space. You've already decided your favorite space to do math in. You want it to like stay the same, like the outer shape of it. And because of that, like you need to. So yeah, sure. Let's just start talking about this algorithm. So this algorithm is doing exactly what Jesse suggested here. We want to run like the first method, like this density increment, until we find some like one pseudorandom part, and then we just kind of grab that and set it aside. So we take specifically, we're going to take all those points from A and like kind of imagine deleting them, like. And then at the end of this, you'll get like okay, ignoring the error part depicted outside of all these guys, you'll get a partition of A. Like it won't be a partition of the space. You have these overlapping container sets, but it'll be a partition of your set A, such that each part is assigned to one of these container sets in the cover, and they're all pseudorandom relative to those container sets. Okay. So great. Yeah, this is like this third construction I wanted to highlight, and then so what does this buy you? Like, okay, in some other settings it buys you more, but in this setting at least it buys you at least this quantity d over epsilon again. So we recover. So now this statement is strictly better than my first statement. Okay, here's a fun. Fact, bonus problem if you like. I didn't actually add it to the exercises, but this statement here, it actually directly implies the level 1 inequality. Now the level 1 inequality is like super easy to prove by other means, so it's not like a big accomplishment, but it's a nice like kind of conceptual point that in some sense this is just like a more specific kind of it's only more information than the level 1 inequality. It's telling you it's true because of this decomposition is possible. Maybe I guess it's like explaining, it's like it is accomplishing this dream of reducing, like solving the problem by reducing it to some specific structured cases. So like the level inequality, you can imagine one inequality is like true because dense sets can be kind of organized in this way with these bounds here. So.
It seems that you get much better dependence on epsilon here, so it seems a bit true.
Yeah, okay, that's true. I guess, yeah, I don't know how to say easily, but how can I say it easily? I don't know. You will probably just have to do the calculation. So for example, I've tried to do it with this bound just to see, and this gives you like a level 1 inequality with, well, this version of the level 1 inequality with epsilon cubed. I don't think it's not clear that it's good enough. Okay, the reduction is not that obvious. Why? Like, it doesn't like immediately apply. You gotta do like, you know, 2 or 3 comparisons to actually say like why. Because right, so like if you want to prove the level 1 inequality, it's about the original set, and then it's not immediately obvious how that like relates to this. Like, you could think of taking your original set and like writing it approximately as some like convex, you know, some mixture of these nice distributions that you obtain from this. But then, yeah, it's still not like, it takes like a little calculation to actually derive what's being, you know, related between the two. Okay, great. And then, yeah, so I got one more of these to show. So here is some like global structure partition. This is like a Semiretti style decomposition where, so what's being gained? The thing that's gained is that like the structure of our overall partition is much nicer. Like it's specifically this like axis aligned partition. It's given to you by some, oh, I guess I'm thinking of the, yeah, you'll see also like in the exercise I have some like rectangle case to look at, which is like very faithful to the actual, like it's basically equivalent to the Semiretti regularity lemma for like bipartite graphs, if you like. You can see that in the exercise, and it's roughly like actually the same proof as well. And okay, so you get this nicer structure. You also pay for it. So this is now the bound on R, like this codimension. So it's like the number of queries that we're going to have to do. And I guess maybe I actually do want to not spoil exactly the trick for obtaining this particular bound. But yeah, roughly it's like, you could imagine it's a bit like the decision tree that we were looking at earlier. You just want to insist on it being non-adaptive, so like you kind of are just forced to make more queries than you wanted like everywhere. And that just blows up big time when you want to iterate that, and this is what you can get. So great, okay, so this is some fourth kind of partition. Here's like, I guess all of them just one more time if you want to compare the quantitative aspects. We had these two that are kind of comparable, giving you this like 1 over epsilon, this like local like protocol style partition. It's giving you something pretty comparable, some like d over epsilon squared control, or you know, like you can have this Semiretti style partition. I mean, unfortunately, a lot of like applications say in extremal combinatorics they really need the structure provided by this Semiretti style partition, and it's really unclear like whether it would even be useful to have this kind of local like protocol style partition, although this shows up like a lot more in like the CS applications. I mean, maybe like sort of necessarily because of the quantitative aspect. Oh, sure.
Can you explain again the difference between
2 and 4. Yes, so this, it's giving you, well, the way I stated it was just some arbitrary partition into structured sets, although you get a little bit more structure from it by following the proof I suggested, that you get this tree-like decomposition. In 4, it's like we want to find some specific set of coordinates, and we just define the partition exactly by taking all the possible restrictions of that set. It's like it agrees, like all these subcubes we're obtaining that it like are aligned like globally.
So in the tree, you didn't fix the same coordinate?
No, so we were, yeah, so in this tree, like it might be the case that like, you know, I guess it's depicted here, like now the problems like decouple, so Like I can continue trying to partition A inside this space and the A prime inside this space. They're kind of like no longer necessarily related, and I have this flexibility that I can now make a different cut on each side, yeah. Oh.
So I think this is what I was confused about earlier when I was asking. So when you, like one naive thing to do would be to say, okay, well, let's just take, in this entire tree, there's at most 2 to the r queries, 2 to the depth queries being made. And so let's just make partition on all those 2 to the d coordinates, which gives you an exponential blowup, but doesn't give you a tower blowup. In the graph setting, that gives you the weak regularity lemma, I believe. Doing that argument gives you like the freeze con. What in your statement of variant 4 is capturing the kind of more Semirati style strength of this, as opposed to weak regularity, something that requires the tower?
Okay, I see. So weak regularity is kind of not the right thing to compare to all the rest of these notions. Like it's like giving you a global quantification of pseudorandomness. Like the definition.
Averaged over the.
Yeah. Like so, the definition we always wanted was this. Like I'm willing to suffer some error. Like I have some bad parts, but when I find a good part, I want that to have like a local description. Like I can just think about. I get some. Per part and like zoomed in quantification of the pseudorandomness of just that part inside its container set, and like it's that which costs you so much if you want this kind of global style partition. Sure.
Thank you.
Well, so if you do that, you get a partition which gives you a good model of, for every coordinate, what the average value of that coordinate is, by like averaging the values that you get in the different, there's different distribution on leaves, and each one either has a fixed or has a number. So, but it won't be that every or most leaves for every coordinate have that right value. So it'll average out over all the different leaves, but it might not be. Exactly right at each leaf, or even most leaves.
So it's like a swap in the quantifiers with the
exactly.
on the, over the coordinates.
So it's just So
pieces.
like in the weak regularity, for every cut, it gives you a good estimate, but in the different partitions, there might be cuts that it gives you a bad estimate for.
Thanks.
Great, thanks. Great. Okay, so yeah, these are the ones that I chose to highlight that have some nice they're comparable to each other, have some nice simple descriptions or like analysis that you can see in the exercises, and then. Yeah, the main thing I want to just reiterate once more, it's like a fairly generic, I guess you maybe believe me already about this point of view, in the sense that you can kind of swap out your favorite notion of structured set. Could think for a little bit about what seems to be necessary about the family of structured sets. It seems like probably you'd like them to be closed under intersections, say, is some abstract quality you'd like them to have, but like beyond that, it's a fairly general kind of approach that you could apply in different situations. And there, in the exercises, I show at least like 2. So there's this one, and then there's some like graph theoretic instantiation of all 4 again. Great. Okay. So yeah. So what did we do? Mostly in this lecture, I mean, it just introduced the ideas, like the high-level ideas, structure versus randomness, and then we talked a bit about this first, like, important aspect, the actual algorithmic part, the constructive part, doing this decomposition, obtaining these pseudorandom properties that are possible to force. turns out that like, yeah, like I don't know why necessarily if I have like a good intuitive explanation of why this is the case, but it kind of seems often like there's only so creative you can get with how to seek better decompositions, like better algorithms, like to improve that side of things. And most of the like real work is on taking like whatever you just are delivered by like the guarantees given to you by these constructions and trying to show that they're actually like useful for something. I guess I can elaborate on this quantitatively. I think it would be nice. Maybe I'll go over here. So I'll talk about like what does this look like for bipartite graphs. So I have like two pictures to think about. One is just like the same abstract picture I always draw, but then you could think like, so if I think of some bipartite graph with some two parts x and y, and I think about it like in two ways, like one, it's just some subset of a product space. And then in this case, we're going to do this like density increment and find some subrectangle that's regular. Okay, so just like before. So what does that look like for the bipartite graph? It's just like finding some induced subgraph that is pseudorandom in the sense that, well, it's pseudorandom with respect to rectangles. Like I guess by definition, it's saying that locally this induced pseudorandom graph, it's pseudorandom in the sense that it satisfies an expander mixing lemma, like it has low discrepancy. You can also, if you quantify it slightly differently, you can get like spectral control as well. So you could obtain some, second, like bound on like the second singular value. But it's nice to see, like quantitatively, what are we actually getting? So if you have, let's say this setting, you have the size of your graph is like this here. Then the quantitative picture that you can get for your spectral control, like the singular value, is kind of like the same thing that you get here. And specifically, I want to say like if you need to be asking for some second eigenvalue like epsilon, which is not so small that you won't terminate before you lose all your graph. So let's say we're trying to insist that this x prime, y prime were this size, which is a reasonable case to think about. Then actually we could, this is like the best thing that we can ask for. So if we want like what's the most pseudorandomness we can get out of a density increment argument, it's like roughly like this. Same. Okay, so and just to remind you, so this is like regardless of the degree of your graph. So like if your graph was like super dense, even like reasonably dense, you maybe would like. Let me start using lambda here, I guess. So I'm saying that this is like is obtainable by density increments. So sure, so the strength of this statement is that it's entirely generic. You're given like an arbitrary dense bipartite graph. You can find something that looks vaguely like an expander in a weak quantitative sense inside. But yeah, like you could.
Are you calling that a weak quantitative sense?
Because of this, because like maybe let's say even the degree is like x over 2. Yeah, and then like I'm thinking of like Alain Bapana, like I'm saying, what could you hope for? You could like the most, if you gave yourself an explicit construction of this size, which was this dense, you could hope for something like this roughly. so like an exponential gap between these two quantities. So that like kind of also explains things like, so in like Roth's basic density increment argument, he gets like this weak quantitative guarantee to work with, and even though like in the problem, like the 3AP problem, it was like open for a long time. There's like big, like nearly exponential gap that it seems like you need something like much stronger to obtain it. So yeah, I just wanted to highlight this as some like limitation that we're always having to deal with when we're using pseudorandomness coming from these like algorithmic decompositions of arbitrary objects. You just like apparently cannot ask for very much for at least in terms of like this specific quantitative measurement of error. We'll talk about a couple different ways that we can think of like some different pseudorandom quantities that are a little bit better behaved if we want to like measure, say, error in like a multiplicative sense. I shouldn't say that now. I'll save that for the next week. But yeah, anyway, my main story here is that, yeah, if you made the expander yourself, you could give yourself this. If you got the expander from this density increment approach, you can ask for at most this here. So, oh, sure.
And this is true also if you, is it true also if you use more combinatorial measures of expansion, like jumbledness or randomness?
Yeah, like, so I guess if you, I can't always keep track of all of them, but if you just mean like discrepancy with respect to rectangles, then
yeah, just I mean they differ maybe in what you put on what you scale the error by, square root of this sizes of the sets or.
Oh, I see. Okay. No, I mean that actually matters. Like in the sense that, okay, maybe I will write this other quantification. No, it'll be too much right now. But like, yes, I think that the answer to your question is yes. Like even if you ask for something weaker, like basically, one version of your question is, are these abstract decompositions I showed you like generally like best possible? In the rectangle case, I'm like very sure they are. So yes, like it would okay, you'll have to see the exercise for what my definition is, but yeah, I've just used like discrepancy in the like communication complexity sense. Same thing I think as jumbledness maybe, but I might not remember exactly what that corresponds to. But, oh, sure.
So this lambda at plus 1 over n, there's an example where this is sharp?
Yes. Yes, there is. Okay, wait. Okay, fine. Let me be careful about the claim. In the like abstract setting that we're working with, like say, if you want an argument that works like generically just for collections of structured spaces where like say all you ask about them is that they are closed under intersection. I think like the density increment argument works like applies to that setting. It's like it's, generic enough that it applies to that setting. In that setting, it's best possible. I really think that in most settings it's best possible, but I haven't you would have to go check them all separately. Yeah.
So it's best possible for your balancedness example before. So doesn't that extend?
I think that's also true. Yeah.
That's true.
Oh, you're saying it. Okay. Yeah. Okay.
So that yeah.
Okay. Yeah. Okay. That's a more concrete example, I guess. That's true.
Zander, I have a question.
Sure.
At what point does this, how dense does the graph have to be in order to, when you're starting, in order to apply this?
When you're starting?
Yeah, you said the degree was x over 2.
Oh, okay. That was supposed to be an example of the most generous thing that I would give you. So, yeah. But I would say. I mean, usually it kind of it's a hard question to answer. It's dependent on the application. We always would like to be able to say non-trivial statements about sparser and sparser objects. I think until recently, there are very few statements of any form, in any space, finite spaces of size n, that were able to say non-trivial things about like density lower than 1 over log capital N. So like, yeah, this like 1 over little n kind of quantity. In fact, like, yeah, so I guess for a long time, this corresponds to this exact threshold needed to show that there are 3 APs in the primes just by virtue of their size. Like if you just wanted to prove a bound for the 3 AP problem, which was good enough that it would imply it for the primes. That was only solved like fairly recently by Thomas Bloom and Olaf Sisask. They needed to like handle sets which are size like, or their density is like 1 over log n, 1 plus like some little constant is what they needed to do to obtain that. So and then, I mean, afterwards, like, I guess, yeah, in my work with Raghu and some of the follow-up works, we managed to start being able to handle some situations where you have sets which are density, which are like quasi-polynomial in n, as in they're like this density 2 to the minus some log n to some small constant less than 1. Yeah. But yeah, I think it's not always easy to say like there's no hard threshold. I guess mostly is like, can you get anything useful, from this kind of argument before it like terminates at a single point? Yeah. Sure.
So just where this is coming from, in the examples you gave us, if we take epsilon to be like 1 over n or 1 over square root of n, then the bound on R becomes trivial.
Yes,
That means
right.
you have to fix all the coordinates and we get
Right.
one. That's where this,
Absolutely,
this
yeah.
log is coming from.
Yes, that's what I'm saying, yeah.
If I understand correctly, for bits, it's just majority, and we just if you take the set will be the majority.
Yeah, that's true. So that is also another, maybe that's your point, tight example for this level 1 inequality that I showed. So we talked about like, are there other tight examples besides just specifically fixing some D bad coins and everything else is random? Turns out for like if you set the bias correctly, I guess it's slightly different than your example. If you set the bias correctly but the same in every coordinate, you can also get a tight example. And then in this case, it seems maybe less plausible that the naive version of my statement is possible, that you can get some like partition into parts that are like, well, maybe that's a bit hard to explain with what I have set up. So anyway, that's some other tight example that looks much different than the first one, yeah. Yeah, sorry, it's like in Ryan O'Donnell's book, there's level K inequality. I guess, what is it? Maybe if you'd like to know what it is, I guess I probably remember it. So this is, yeah, so the level K inequality. Is I believe, roughly this bound. Yeah, so maybe the trivial bound would be n to the k or n to the k over 2 something. And then this is what you can get for dense sets with entropy deficit D. Yeah.
You have to know, right? So it cannot be.
Okay, I'm sorry. Like this is my convention, like A is 1A over delta. Does that explain what you're saying? So this is like normalized as a density function. So this is 1.
bias of the data?
Oh, yeah, this is literally, so this is like the Fourier coefficient. So the Fourier characters over F2, they look like this. So this is just exactly this quantity.
Does it imply anything about the bias of the data? Like how many data points have certain bias?
I think it does. Yeah, at some point I was like, because it's actually like pretty convenient to prove this and pretty difficult to prove that like directly. It's like a bit of an ad hoc way to obtain that kind of information, but I actually think it does. Yeah, it's not like I think you're losing some like 2 to the k here is what I'm saying. If that's so it's only like mostly if you cared about like this specific kind of function on this on your subsets XS for all the sets of size k, or you ask the same question but you allowed any function, I think that like, or like any balance function, I think the answer is approximately the same.
As a natural follow-up, can you get structure versus randomness results for level K inequalities?
So you'd have to decide what you wanted, I guess. I kind of set up so that the level 1 inequality was supposed to be some like yeah, some point of reference. Like it's not necessary. A priori, it wasn't supposed to be related to structure versus randomness. It's just something that is true about dense sets. We wanted to see if we could recover it more specifically from some like specific structure versus randomness decompositions. So you could ask maybe, can you prove the level K inequality with any of these decompositions? It's an interesting question. I don't think I've tried to check. Yeah. Any other questions? Oh, great. Yeah, thanks so much. Oh, go ahead.
Go back to the four different kinds of partitions.
Sure.
For which of them do we know? Do we have lower bounds on R?
Okay, I think they're all tight, but I didn't want to promise that. That's all. I'm just saying, you know, they're just I don't think people usually try to. Like people use these arguments all the time. I don't know if people try to like systematically like characterize them. I mean, certainly for Semredi, yes, but like maybe not in every abstract setting, just like specifically for graphs. I think what Claude thinks that this is tight for in the Boolean setting. I didn't like look into it, but yeah.
What is known?
About what?
What's the known lower bounds then?
I'm saying I don't know anywhere where anyone's like written anything about this. Yeah. Sorry, besides for graphs, the graph setting with rectangles is like yeah. Okay. Great. Thanks, everyone.
I just want to say a bit about exercises. So now there's a half-hour break. After the break, there will be exercises. I just wanted to list the rooms, since now we have 5 topics. So for the auditorium, left side will have expanders. Right side will have strong convergence. 116 is actually a fairly big room. On the left side, we'll have pseudorandom.